All right, our next speaker this afternoon is Hayden Campos, who comes to us from Dartmouth College, where he'll be a senior this coming fall. Hayden's been working this summer with Abigail, and he'll tell us today about his project, examining type 1a progenitor channels through carbon-2 absorption features. Go ahead whenever you're ready.
Thank you for the introduction, and I'm super excited to show you all what I've been working on this summer. And before I begin, I'd like to give it a little introduction into what type 1 supernovae are. And type 1 supernovae is a type of supernova that occurs in a binary system with two stars orbiting one another, in which one of the stars is a white dwarf, and the other star can be anything from a giant star to an even smaller white dwarf. Oh, sorry, I'm getting a number alert. Okay, and before I'd like to also talk about the supernovae progenitor channels for type 1a supernovae. And for this, there's the Chandrasekhar mass explosion, which is when the white dwarf reaches the Chandrasekhar mass limit, which is 1.4 times the mass of the sun. And the SUB-CHANDRASEKHAR channel, which is detailed in this graphic here. And the SUB-CHANDRASEKHAR channel, also referred to as the double detonation progenitor channel for the type 1a supernovae, is a mechanism that can ignite a white dwarf below the Chandrasekhar mass limit with a helium shell. And in this case, in the helium shell can send a shock wave into the center of a white dwarf where it can detonate the core. And in this, we expect all the carbon to be burned away during the explosion. However, for an event like the Chandrasekhar mass explosion, we know that some carbon can remain. And it's noted that some supernovae contain a carbon absorption feature, indicating that these events would arise from the Chandrasekhar mass explosion. And just some motivation about why we're going into this is for carbon-2 in particular, we know that carbon is an original feature of the white dwarf, and it's not created in the thermonuclear explosion, such as other elements. And I'd like to also say that carbon-2 is a very difficult feature to measure, as I'll be detailing in further slides. And this is simply due because of carbon-2 being a very small absorption feature, as opposed to other elements such as silicon-2. And as mentioned in some of my previous presentations throughout the summer, we'll be focusing on this theoretical model from the report titled Observational Predictions for the SUB-CHANDRASEKHAR Mass Explosions by Polin et al. In order to confirm our understandings. And in this plot, we have the x-axis as the silicon-2 velocity in 1,000 kilometers per second, and the y-axis as luminosity, which can be best understood as how bright an event will get in its lifetime. And in this plot, we see that we have two distinct subgroupings of supernovae. The first cluster follows this relationship between brightness and velocity that is a natural byproduct of the SUB-CHANDRASEKHAR class of explosions, while the second cluster is quite offset from this relationship and is tightly bunched in the left-hand corner, and is considerably slower given their median luminosity than other models. And with this plot, we're expecting that all the supernovae following this model here will be those that do not have a carbon-2 absorption feature, and all the supernovae that do have a carbon-2 absorption feature will typically lie in this area here in the Chandrasekhar mass explosions. And to give it a little bit extra background, we know that for the previous reports have tried to distinguish these supernovae progenitor channels with other theoretical models. And these are two examples by Abigail Polin. The first one on the left is distinguishing the progenitor channels based on color, where supernovae that are more blue tend to lie in the Chandrasekhar mass explosion, while supernovae that are more red tend to lie in the SUB-CHANDRASEKHAR channel. Additionally, on the right, we have another separation of this progenitor channels based on nebular emission, where those that are more strong with carbon tend to lie in the more strong in calcium tend to lie in the SUB-CHANDRASEKHAR channel, while those that are more weak in calcium tend to lie in the Chandrasekhar mass explosion area, where the red is. And for this project, we'll be distinguishing them in a third way based on the carbon-2 absorption features in the supernovae. And in order to do such, we've had to modify previous code from the Carnegie Supernova project to include a carbon-2 absorption feature. And for this, we had to determine an appropriate rest range, an appropriate low range, and an appropriate high range And we have a running example from SUPERNOVAE 28Q on the left, where the red indicates the spectra of the supernovae, blue is the pseudo-equivalent width, and in this spectra, we see that the carbon-2 feature is lying around 6,300 angstroms, and the silicon feature is around 6,100 angstroms. And as you can see, as mentioned in previous slides, the carbon-2 feature is notably smaller than the silicon-2 feature. And because of such, sometimes they'd get interrupted in the data set from being not good enough quality and having noise in the data. And for this project, what we've done is we've analyzed a data set of 50 plus supernovae from Zhang and McGuire in order to create this intermediate plot shown here. And for this plot, we have those supernovae in black. The supernovae that are circles are from the Zhang data set, and the supernovae that are in squares are from the McGuire data set, with red indicating that they did have a carbon-2 absorption feature, black indicating that they did not have a carbon-2 absorption feature, and gray indicating indeterminate, which could either be from spectra not being taken on early on in this supernovae's lifetime, or just from being too much noise in the data. And as you can see, all the supernovae that do contain a carbon-2 feature tend to lie in the Chandrasekhar mass explosion area, while those that do not have the carbon-2 feature can either lie in the SUB-CHANDRASEKHAR channel, which is the theoretical model in blue, or they can also lie in the Chandrasekhar mass explosion. And from such, what we've determined is that the presence of a carbon-2 feature can be used to classify type 1a supernovae progenitor channels, and that there's a clear distinction in carbon-2 absorption feature among supernovae arising in the Chandrasekhar mass explosion. And for future work, what we're hoping to do is test our hypothesis and our models on an even larger data set, which is the Carnegie Supernova Project data, which is a collection of 130 plus supernovae, in order to further test our hypothesis and test our understanding. And that is it.
All right, very nice, Hayden. Do we have questions for him? So I guess I'm curious, the Carnegie Supernova Project data that you were mentioning, how similar are those spectral data to the type that you've already been looking at? Do they cover similar wavelength ranges, and are they like similarly high quality? Do you happen to know? I don't know if you've had a chance to look at any of them.
No, I was supposed to look at them this week, but something came up, so I just didn't get the chance to look at it. But hopefully in the coming weeks, I'll get to.
Perfect. All right, other questions for Hayden? All right, if there are no further questions, let's thank Hayden again.